Welcome to the Todd and Noah show, taking the mystery out of electric motors.
Is it October?
Is it October? It depends on what part of the country you're in.
Well, all I know is I walk in.
Some people live in October.
That's true.
They love. I would have never expected Halloween to be one of the most consumer spending for Halloween.
Well, as
I guess
as
for
a father of
costumes,
four,
maybe?
I can relate.
Oh, really?
Oh, yeah. First of all, in home, it's not October. It's August for goodness sakes. And I'm going to Home Depot and Lowe's, and I'm immediately hit with werewolves and things like that. So it's out there. It's heavy.
It's already there.
Absolutely.
I guess you're right. If you go to Sam's or wherever you shop at Target, they're already pretty much putting
a lot of mysterious characters at the entrance.
Do you full out your house?
No. We are, well, when there was more children there, we considered the whole smoke out of the front, ice. And it was pretty cool, really. But now it's pretty casual.
Yeah, we used to do that scarecrow thing that on the broom handle or something.
Oh, yeah.
It freaked me out because I'd look out the front window thinking some head is like,
who is that?
Goodness,
I put that there.
It's just a scarecrow man from Michael's or wherever we got that from.
Well, motor testing is not that scary.
No, it's not. And it's not really, what a great segue. It's not supposed to be scary because we're trying to take the mystery out of electric motors.
Right.
And this podcast today, we're going to focus on insulation tips. Now, that's a big part of the power circuit. It's a big part of the fault zone. It's one of 6 fault zones, but the insulation is kind of what keeps the water in the pipe, so to speak.
And it's blamed on everything.
Everything is an insulation issue.
The motor smoked and it went to ground.
Failed insulation.
Usually the phrase. And insulation changes from, here in sunny Tampa, Florida, or Arizona, right? The humidity level is very different. Right now in the Florida area, we wake up with 100% humidity every morning. And it burns off to a lower percentage in the middle of the day, but the feels like temperature is around 100, right? So, but if you go to Arizona, it actually is 100 degrees.
Right.
There's no humidity, and the insulation testing is very different. Everything responds very differently.
Yeah, moisture does have an effect. I think we had here's when we had a interesting, not so much case study, but a comment from one of our customers with respect to heaters. Do you need the heaters on in the motor? It changes the insulation resistance to ground measurement so much. And it's kind of like, well, maybe that's why the heaters are there. I'm not sure. It's
kind of like when my kids ask how important is money, I say, well, it's not everything, but I'd rank it up with oxygen, so.
It's pretty high. Yeah, it's the root of all evil, but you need some money to make your life a little easier.
Yeah. The sad thing about heaters is heaters do a great job, right?
Yeah.
Electric heaters inside of a motor, by design, they burn the moisture off, maintain the insulation above dew point, and prevent condensation from forming on the wings.
Because when condensation gets into the insulation and say that insulation cools down, it kind of like sucks in all the contaminants.
Like a vacuum.
Yes.
And when that moisture gets in there and you start that motor under a contaminated insulation environment, you're laying groundwork, like putting bricks down for the step out the door.
Little traces that could potentially go to ground, and then the motor doesn't start anymore because it takes the path of least resistance. So this first one, November 22nd, 2011, insulation resistance profiles. What's an IRP?
So an IRP, as listed in the IEEE 43 standard, is an insulation resistance profile. We call it a PI, a polarization index. And here's what's different. A PI is an index number. It's designed to be a quantitative value. A 10-minute resistance to ground reading divided by a 1-minute resistance to ground reading. Now, a profile is, instead of just taking those 2 quantitative measures and coming up with a number that's good or bad, we actually continuously record the insulation resistance over a whole 10-minute period of time. So we're looking at the graph or the profile of the change in resistance, and that can be just as powerful, if not more powerful, than a simple comparison of 2 values.
So we measure every 1 second, and we graph it every 5 seconds to
Yes.
kind of give you a visual look.
Yeah.
Because, like you said, the profile is the 10-minute and the 1-minute. You ratio those two together in something between 2 and 4.
2 and 4 is considered normal and healthy for a polarization index value.
Right. But what happens if 3 minutes, 4 minutes, 5 minutes, some kind of discharge occurs? That doesn't ever get added up in that PI.
It doesn't. Unfortunately, the standard calculation, if it recovers by 10 minutes, and let's say the 10-minute reading is 1,000 and the 1-minute reading is 500, then you got 2. And if you're not looking at the profile, you think you're good when you're not. And that's such a big reason why this got incorporated into the standards as an additional tool.
Yes, there's no replacement for a graph or something that shows some kind of discharge or breakdown. August 31st, 2009, temperature or embrittlement?
Happens all the time.
Yeah. Greater than 8. What's a PI greater than 8? And
It's
what
one of
could
two
cause
things,
that?
just like you titled it as a tip, temperature or embrittlement. All right, so embrittlement is the hardening of insulation. And again, if you see a PI that just continues to rise from 0 to 10 minutes and it calculates a PI value of 8, right, you have to be concerned about embrittlement, right? And so the issue that we always follow up with that is, hey, what kind of maintenance has been performed lately on this motor? Has there been any overheating, right? If you've had a single phase environment, these are the kind of things, or is the motor 20, 30, 40 years old? Some of the original motors designed and lasted a long time. And as a result, they may be exhibiting an embrittlement. Now, to take you a little deeper into the world of embrittlement, if you look at the insulation at a microscopic level, there are little, basically molecular structure that make up insulation.
Domains, or what are they?
Their domains is certainly a way to look, but it's like the molecular structure of the individual,
Positive and negative.
right? Almost like little ions. But so in normal state, they're a disarray. That's what makes them a dielectric, right? It doesn't conduct. It prevents current from flowing. But if you charge it with a DC signal, well, they line up, right? And as a result of them lining up, that creates, it's how easy is it to line that molecular domain up, tells you how quickly the insulation charges. Well, if they're very viscous, if they're aged and old or overheated, the alignment of that molecular domain becomes real sluggish. It's really slow, and that's what we're looking at, right?
Like getting out of bed in the morning, the older you are.
Out of a car.
Sluggish. That's right. Out of a car that you've been in for 2 or 3 hours.
That's right. Driving down here to sunny Fort Myers, I have to think about getting out of the car.
Domains aren't lining up
That's
correctly.
exactly right.
That's what you can say
a little
now.
embrittlement.
You're like a PI of 8 getting
That's
out of
right.
the car.
It's a good example. So now on the flip side, and we see this a lot at tech support, someone will send in a polarization index test that not only is going up, it's going up in a hyperbolic method, right? Like it's ramping up. And that often is not an issue of embrittlement, but a false indication of embrittlement. It's actually a temperature change. Earlier in some of the tips and podcasts, we talked about temperature coefficient, right? So if there's a positive temperature coefficient, like say copper wire, like if you heat wire up, the resistance goes up. So it's a heat goes up, resistance goes up. If heat goes down, resistance goes down. Well, guess what? Insulation has a negative temperature coefficient, right? It's not positive, it's negative. So as temperature goes down, resistance goes up. Well, when does the motor temperature go down? When it's turned off.
Yeah.
So let's say that you're in a shutdown situation. The operation says, hey, we're going to shut this down for 1 hour. You got 1 hour.
Yeah.
Get your test done. Well, that motor's never going to cool down in an hour, right? So you walk up with your MCE, you're ready to go, you hook it up, you're doing all the testing, and literally the temperature is racing down. Well, again, negative temperature coefficient. As the temperature is dropping and you're trying to do an insulation resistance test, the resistance just keeps going up and up and up, and you can't keep up with it. So basically, you end up with an 8 or a 10 or a 12 PI, and you're like, oh my gosh, we got a problem. In reality, it's just a temperature change.
Right. And so that gives us this negative temperature coefficient. April 19th, 2010, you kind of explained the negative temperature coefficient. This means that as the motor temperature rises, like in normal operations, that the insulation resistance to current flow reduces.
Yep.
So as the motor temperature goes down, when it goes through shutdown, the insulation to ground or resistance to ground measurement goes up. Now, we also talk about here the 10 degrees Celsius. For every 10 degrees Celsius rise in temperature, the resistance is cut in half.
It is indeed.
So
yeah.
that is the thumb rule.
That's a good quantitative measure. And there's a couple other, what's interesting is not to be confused with, over temperature,
Yes.
right? So if you exceed the design temperature, this is estimates coming in from designers basically, but if you exceed the design temperature by 10 degrees, you cut the insulation life in half, right?
Not just the value like it is here
right.
on a
This
negative
is
temperature coefficient. It goes down 10 degrees.
Right.
Resistance goes up by twice.
Right. Absolutely. So it's a very similar ratio, actually, exactly the same for different reasons. Right? Different subjects.
Once you get to the Class B, Class F, Class H, limited, 155, 185.
Gets up there. It can be
Celsius,
a lot hotter than you think. Yeah, than most people think.
Yeah, but
That's
once
hot.
you exceed that by 10 degrees Celsius, if you get to 165 on a Class F insulation.
You're cutting your insulation life in half.
Could be.
Yeah. What's interesting is if I were to take you back
to the Wayback Machine.
Wee lad,
the Wayback Machine.
Right. 100 years ago, AC induction motors were ginormous, right? Which is an interesting word. So you could lay your hand on a motor in the field as sort of a normal reliability test, right? You lay it down. Okay, it's okay. If you could leave it there, what's the rule? Like 5 seconds. If you could put your hand on a motor and leave it for 5 seconds, it was okay.
Mm-hmm. So much iron.
Right. The thickness of the iron back then, a 100 horsepower motor was huge, and today a 100 horsepower motor is not that big because they've made them so much more efficient. All the heat is removed rapidly to the surface of the iron of the casing and dissipates into the air.
Blown away.
So good luck putting your hand 5 seconds on a motor today. I'm just saying, don't use that 5-second rule anymore as a basis on whether it's too hot or not, because it's very different from the old and new.
Even your pool pump motor is highly efficient. You don't want to be putting your hand on it. It is extraordinarily hot.
It discolors the paint. It's that hot.
Surface moisture and the insulation system.
Oh, we kind of broached that a little bit with Arizona versus the
December 12th, 2011.
Florida.
But what you're to kind of reiterate, if it's a wetter environment, you potentially could have lower resistance to ground versus a drier, less humid environment.
Yes, we try to make sure that you're not jumping too quickly to a conclusion based on a natural environment. So if you are taking a test and you're used to, 100,000 megohms of resistance to ground, and all of a sudden you show up and you test someday and it's 20,000 megohms. Again, check the heaters. When the motor's not running and you're doing resistance to ground testing, heaters should have been on and drying out the insulation. It's not necessarily time to replace the motor, but you need to figure out, what's creating that drop. Now,
and I think here we're talking more about normally the absorption current significantly influences the insulation resistance profile.
Good point. Yeah, related to the IRP.
Yeah.
So as you have moisture, if you think about the three currents that flow through or around an insulation system, when you charge it with a DC motor, you have that initial charging current, which rapidly, up in steady state, right? That's just establishing a positive negative charge over the insulation. Then you have what we call the polarizing current, right? Remember we talked about the molecular domains lining up, right? That's the polarizing effect. That's current going through the insulation. Then you have surface leakage, right? Mm-hmm. And that's not supposed to be the dominant thing. But if it is a dominant thing, then what you end up getting is a rapid rise.
Kind of trending down, maybe not drifting towards infinity, or just stabilizing.
More likely stabilizing, unless there's damage. But what it ends up doing is you have a rapid rise to a certain level, and then it just flatlines. And a flatline PI is basically 1, right? If 10 minutes 1,000 meg and 1 minute's 1,000 meg, the value is 1, and that's much less than 2. So a lot of times you're going to flag a polarization index test, an IRP test, you're going to flag it as a failure in the vicinity of a high moisture environment. So something to be aware of. So
this next tip, August 18th, 2014, temperature limits. We talked a little bit, but this is getting into the National Electrical Manufacturers Association has established the average insulation life of a motor insulation based on maximum operating temperature to be around 20,000 hours.
That's a lot.
NEMA classifies insulation into 4 different Class A, Class B, Class F, Class H. And they have temperature assignments around each of those. So you expand on that a little bit. We already talked about it somewhat.
Yeah, for the most part, we design a lot of our limits and our thought processes around, the classic, H is a very popular insulation out there, to be honest with you. In fact, you'll see a lot of them that will be listed as Class F,
Right.
even though they got a Class H limit, or they have a Class F limit, even though they're considered Class H. And a lot of times that's because the tape or some other auxiliary that doesn't have the high temperature. So, these are numbers worth being aware of. There's surface temperatures and then there's internal temperatures that, you can't just, measure the external and think that you've got, most companies when they have critical motors are going to have the shops install RTDs into them so that you're actually getting into the slots and into the measurement point where you can actually maintain that. And again, referring back to our reference earlier, for every 10 degrees over the design temperature, you potentially cut the motor life in half. That's how much degradation occurs beyond the set point.
Beyond that, 155 degrees Celsius or 180 degrees for Class H. Step voltage testing is designed as a controlled overvoltage or proof test to provide an additional evaluation. This came to us May 11th of 2009. We document this through IEEE 95.
95. That's the high voltage standard.
That's the high voltage standard. And so we provide, we do a PI, and then we also can do a step voltage. And some of our customers do them back to back, but necessary or?
No, and here's the thing: is some companies have microamp limits on their, and so they actually classify a limit. So, like we have a utility company that has a specific microamp flow of current during RTG testing that makes or breaks the decision to do something. So they're going to do a step voltage no matter what, because our RTG testing is just a resistance measurement. We don't actually, record the current. Maybe something we should do. But, from a step voltage.
Well, we do the inverse, which we record.
You could calculate it, certainly.
Insulation.
Right.
Resistance,
right. So,
And we the difference is we apply it steady to the PI, and then we incrementally step up the voltage.
Right. In general, it ends up taking about the same time as a PI test, about a 10-minute
6 minutes,
run.
or is it 10 minutes?
Well, it ends up being, 6 to 10 steps of a 1 minute, right? Depending on what voltage increment you decide.
Okay.
And there's no hard, limit or requirement, but in general, it's between 6 and 10 minutes. But I kind of like the test because, like I said, the only thing that you don't want to do is the step voltage test normally follows. You want to start the step voltage test once you've already polarized the insulation. So you're going to apply some form of polarization index test or polarizing voltage, and once it's stable, then you start on your step voltage test. Now, of course, you don't want to start your step voltage test at a lower level than your polarizing test, or it's going to go backwards, right? And that's not good. A step voltage test is supposed to step up in current. So as you apply more voltage on a 1 minute increment, then the current should go up with it.
Current discharge should go up, but linearly.
In a linear fashion. Good point, right? So if for some reason it's going up in a nonlinear fashion, it's a problem, right? And that's where you're seeing, with higher voltage, you're seeing a nonlinear reaction in current, and that's indicating weakness of the insulation system.
Destructive versus non-destructive testing, we hear this a lot. We're not opposed to high pot testing or even surge testing in the correct location.
Right. If I was a motor owner in a plant, I wouldn't dismiss that testing at all. I would expect it on a QA level. I would be very tightly, before I accept the motor, I'd be very tightly controlling of it in the field. It would have to be, any type of overvoltage stress testing. I want to keep that at a shop level. And that's not to say might not be occasions where, there's just something, some odd little fault is just not showing itself, in which case the only way to figure out what the root cause might be is a stress test. But usually that's not the right answer. So it's, it is, for the most part, all the standards will tell you, hey, use standard trending, insulation tests to identify, weakening insulation, reserve the overvoltage stress testing for OEM, quality control, that kind of stuff. And that's our position on that. And again, if anytime I refurbish a motor or whatever, I want to perform some overvoltage testing before it comes back out of the shop.
Okay. How much high potential testing? How much is enough? This was a tip that came to us February 20th, 2012. According to ESA AR 100 2010, it gives a set amount of voltage that you should put in there. Is that still true?
It is, yeah. And these are standards that you want to keep up with. One of the things we try to do in our tip of the weeks that we send out is if there's a change in the standard that affects our end users, we try to share it, right? Well, we don't, our over voltage testing is usually reserved for a step voltage test. And again, we do that on a controlled level, occasionally in a deeper troubleshooting level. The basic approach, if you talk about 2 times, line voltage plus 1,000, is really reserved for the OEM, right? It's reserved for the manufacturer or OEM, and so once it gets in the field, all that changes. And that's the important part of that is, you want to, cut that down to 0.6 times the standard, and there's just a lot lower values that you want to apply. And again, once the motor's contaminated and the insulation is no longer considered clean and dry, it becomes real questionable as to the right approach to overvoltage testing. They're going to suggest you kind of stay away from it at that point.
Okay. August 10th, 2015, testing insulation with DC voltage. Just before the turn of the 21st century into possible role of the DC testing, what they found was that not all distribution cables responded the same. Polyethylene insulation was found to be far more susceptible due to the space charges that developed in localized areas of the PE resin. This charge gets stored and adds to the peak stress voltage seen by the insulation during a surge or the next AC motor start. Additionally, these cables are often run underground in potentially wet environments. This can create water trees to form in the insulation, further weakening the insulation system against the elevated peak starting voltages.
When we were driving down to Fort Myers today, we saw an amazing electrical light show.
Yeah.
It was incredible. And if you've never gone online to Google or whatever and look up insulation treeing, you need to do it. It looked just like we saw in the sky. I mean, for repeated, voltages applied across insulation systems, especially in moist environments, it creates this amazing looking tree of carbon tracing through the insulation system. And that's what they're trying to say here. And especially if you're dealing with, the polyethylene types, the XLPE insulation systems, the way they're built is they hold a charge, right? And so this becomes a big deal. Mm-hmm. One of the things that even with our test equipment as a reliability trending tool, right? If you got a 460 volt motor, we're going to apply 500 volts for insulation testing. If you got a 4160 volt, we're generally going to start with 2500 volts, right? You think about the line voltage and how it's used. But the one thing that they learned in this situation is that depending in cable runs is what we're talking about here, right? The XLPE, the polyethylene stuff. Certain types of cables hold that charge very strong, right? Mm-hmm. So you put 5,000 volts across that cable to ground, it doesn't just go away. And here's the problem. If you got, 4,000 volts left on that cable, minutes after you stop the testing, and plus, many minutes possibly. It takes 4 times as long as the charge to discharge naturally, right? If you just leave the cable alone. Well, if you have, 10 minutes later, they decide to push the start button on this motor with XLPE insulation cables or XLPE cables, think about the voltage hit it's taken. It's got 4,000 volts still on the cable run itself, and then you're adding another 4160 volt AC on top of that. You can see the destructive possibility here. And so anytime you put moisture in there, it creates this treeing effect and a potential catastrophic situation. We were talking to, one of the government agencies involved in aerospace, right? And they used to do high pot testing of cable runs every year. And they would blow cables up all the time. Yeah. What they come to find out is that they're putting this DC high pot across these cables in very moist environments, and they're already. And so that treeing, when you apply that DC and you start to polarize and you start to trace these carbon traces through the insulation, every time you do it, it gets closer and closer. Now, dry insulation, dry cable's not a big deal, but even with our PI test, if we think that you're performing a PI test on a cable underground, we strongly advise inspecting for water. Yeah. And there's no reason to put a 10-minute PI on a cable if it's already failing. In other words, if you say, hey, this is a bad test, don't leave it for 10 minutes. There's no reason to further potentially push the treeing effect into the insulation. And when it comes to starting a motor, That's a pretty big deal. We always try to emphasize this: discharge this motor. So we try to work to discharge that at the end of each, DC motor test. And if it's not happening, you stand a chance of putting 8,000, 9,000, 10,000 volts across that insulation on the push start of the motor. So you control that tightly. I think it's important.
Mm-hmm. Speaking of water, submersible pumps, they have a lower resistance to ground because they're in water.
They are, yes.
And any other precautions that you would take with submersible pumps? This was a tip sent to us by one of our customers out of the Metropolitan Sewer District of Cincinnati.
Yes, in general, we try to defer them to the manufacturer, right? We always suggest, hey, you should probably defer to the manufacturer. There is the Submersible Wastewater Pump Association. New motors installed in a wet well assembly can go as low as 2 megohms. So understand what you're expecting.
Know the process, know the application, and know what the requirements are, the specifications are. And
again, because it's a moist environment, get the reading and get out. Yeah. There's no reason to stay
QA
in.
is important there.
It is, absolutely.
Make sure that the motor that you're putting in and the power circuit that it's attached to is pristine.
Absolutely.
Here's one for DC, correlating current, armature current, and insulation. It was interesting. The armature, because it flows in one direction, so we would do A1, A2, and if there's any gap between the two currents, then it's going somewhere. Does that correlate to insulation?
It does, and it can.
It's not something we go out and pull assets on, but it's
not usually.
Certainly
it's
something to pay attention to.
And it'll prompt the use of other tools to try to confirm the condition. This really set in on the locomotive industry. Right, yeah. It used to be a lot of DC traction motors and stuff, and they would measure the current in and out, right? And as long as there wasn't any kind of sensory, technology that could pull current away, certainly like heating elements or auxiliary power or something like that, transformers that could be in the circuit. You need to know that, right? But current in should be current out, right? Yeah. And a differential current, and we set an alert at 5%, right? If you see that differential, we want to alert you. Now, again, just like you said, we're not going to base a final decision on that. We're going to say, hey, we got over 5% differential current. Look at the circuit, see if there's anything on a parallel load. And if it's not the case, then you need to next shut down, get in there, do a polarization index, do a resistance to ground test, see what's going on, capacitance to ground, all the above.
And then I'm going to end this with our last one, May 9th, 2016. Heat is the number one killer. I always hear you say that.
It is. Yes, the number one killer of motors is heat.
And we said it because of the types of insulation classes. They have a specific temperature that they can rise to. Anything above that.
The thing we like to remind them of, yes, that class is important. If it's 155, if it's 180, understand what your limits are and stay within it. But the thing we like to remind our customers of is almost all of our fault zones lead to heat. Right?
Yeah.
Rotors lead to heat. Stator leads to heat. Eccentricity can lead to heat. Right? Power quality leads to heat. Even right? Harmonic content leads to heat. So heat is the number one killer. Now, what you want to do is find out the root cause of what's leading to that, and make sure and take care of it.
Like you said, in harmonics, you want to find out the voltage harmonic content, current harmonic content, and get filters in there, and get that out of there because it's doing very little work and giving you heat in the circuit.
Right. You're asking a 100 horsepower motor to deliver 100 horsepower, but because of poor power quality, you're only giving it 80 horsepower worth of energy. So what it has to do is run 120 horsepower, which is excessive, right? So it runs harder than it should to deliver the same 100 horsepower because you're wasting it through power quality issues. So it all comes down to heat.
Yes. And we'll end it on that. It comes down to heat. That can destroy your insulation system. So once again, thank you. Thank you for joining us as we went through this Insulation Tips podcast. If you have a tip that you'd like to share with us, I'll be more than happy to look at it and add it to our plethora of tips. We started 2007 is when we started putting tips out there. It's now 2024.
My goodness.
That's a long time.
That's a good series.
That's a great
series. It's hard to keep it at a weekly frequency, I'll tell you that.
We're not quite tip of the week worthy.
Yeah. Maybe tip of the every other week.
Even then. However, anything that you want to share with us, we'd be more than happy to take it. That'll bring us to the end of this podcast. As always, we appreciate you guys listening in for us or listening to us. And if you have any suggestions or comments, by all means, let us know. Until we see you again, have a great day, and we'll talk to you soon.